The Earth System, a video series for educational institutions for free use presented by the German Geological Society, the DGGV. Hello everyone. I welcome the viewers of another episode of my video series on the Earth System. This video is about isostatic compensation in the interaction of the lithosphere and asthenosphere. And as with all other videos, I would like to point out the opportunity to write to me if you have any questions or comments. My email address is written down on the first page of the video or on the website. I showed this section through the lithosphere already as the last figure of my previous video. We see here all types of lithosphere with their respective average densities. And I will now use these data in a conceptual model that I would like to discuss here. For this model, I use the density values of 3.0 gram per cubic centimeters for the oceanic crust, 2.8 for the continental crust, then 3.3 for the lithospheric mantle, and for the asthenosphere we have to assume a bit lower value of 3.25 gram per cubic centimeters because it is warmer, to a small degree partially molten and therefore a bit lighter. These density values are of course average values that are greatly simplified, but for this consideration it makes sense, and well, that's why I'll use these values now. This conceptual model has at its base the isostatic compensation level. I remind you that everything above the compensation level must be in balance. That means it has to have the same total weight. You can see it here in the model that I already explained in the last video. Here you have the same pressure at every point on the compensation level. That is this gray colored plane, even if there are different heights and different materials above it. For this conceptual model, we imagine a column that is 200 kilometers high, but it has a base area of just 1 square centimeter. Well, something like this can only be done in our mind and cannot be implemented in practice. But anyway, it's a good imagination to explain the effects of isostatic compensation. This column represents the average continental crust with a thickness of 30 kilometers. This value corresponds approximately to an average value of the thickness of continental crust. Below that is the lithospheric mantle, which is approximately 70 kilometers thick. And at the very bottom, up to the compensation surface, there is another 100 kilometers of asthenosphere. According to the respective densities, I calculated how much the individual column parts weigh. Here it says 30 kilometers, which then has to be multiplied by the density, in this case 2.8 gram per cubic centimeters, which means a weight of 8,400 kilogram for the column with continental crust. The lithospheric mantle column weighs 23,100 kilogram, and the asthenosphere column weighs 32,500 kilogram. Together, this results in a total weight of 64,000 kilogram. And of course, this represents the pressure on the compensation level, namely on this 1 square centimeter. For further consideration, this value, 64,000 kilogram, is the equilibrium value that must be achieved again and again in this model. Let's have a look at different scenarios. First, we double the thickness of the continental crust, as we can see here, for example, caused by the collision of two continents. As an example, you see here the collision of India with Eurasia. The lithospheric mantle is not doubled because it is partially pulled back into the mantle and therefore does not contribute to the thickening. But the continental crust of both colliding plates remain on top and are stacked. So now we have continental crust on top twice, and as a result, the sum of the 200 kilometer long column changes. It becomes lighter because the crust has a lower density than the asthenosphere. With a total length of 200 kilometers, the column is now missing 1,350 kilograms. And this missing mass must be compensated by the flowable asthenosphere. At a density of 3.25 gram per cubic centimeters, 1,350 kilograms correspond to a column of more than 4 kilometers in height, 4.154 kilometers to be precise, made of asthenospheric material. Of course, the density of the asthenospheric mantle plays a crucial role in calculating this value. By this amount of more than 4 kilometers, the overall column is now longer and raised compared to the original position of the top. More than 4 kilometers. This actually puts us in the range that we observe in our mountains, such as the Alps, Pyrenees or Himalayas. I will explain also why this is sometimes significantly more, for example in the Himalayas. I will concentrate in a later video on erosion and lifting, and I will explain that without erosion, the high peaks, such as Mount Everest in the Himalayas, which is almost 9 kilometers high, would not exist. This next column shows us another scenario. This time we don't put anything on top, but rather take away the entire lithospheric mantle and replace it with asthenosphere. This is what happens when a continent breaks up and a rift system develops with a rift valley. A good example of this is the East African rift, where this is exactly what happens. As the continent breaks up, the asthenosphere rises up to the lower limit of the crust. However, since the asthenosphere is slightly lighter than the lithospheric mantle, the column beneath the rift system also becomes lighter overall in this scenario. Therefore, also in this case, a certain amount of flowable asthenosphere has to be pushed in from below to replace the missing mass. The result is also an uplift in the rift area. It is not as much as in the case of crustal doubling, but here too it is a noticeable amount of more than 1 kilometer, precisely 1,077 meters, which corresponds to a weight of 350 kilograms of asthenospheric material. And also this example is comparable to what we see in nature. At the beginning of a rifting, a bulge rises above a future rift valley that will collapse in the middle of the bulge. This graben structure is also known as the median rift graben. The amount of uplift of the graben shoulders is similar to what we determined from the simple column model. The graben shoulders may raise up by 1 or 2 kilometers with a maximum of 3 kilometers. Finally, to complete the possibilities of isostatic compensation, let's look at the isostatic conditions of the oceanic crust. The oceanic crust is significantly heavier than the continental crust, but it is also much thinner. The water column also has to be taken in account here, and water is significantly lighter. Therefore, with the same thickness of the lithospheric mantle, a higher asthenosphere column must be assumed in order to get back to the 64,000 kilograms of total weight above the compensation level. All of these considerations result in the picture of the lithosphere that I showed initially in this video. If we take the lower edge of the image, not the lower limit of the lithosphere, but actually the straight line down here as the isostatic compensation level, the same overlying pressure prevails everywhere. And if this balance is disturbed by plate tectonic movements, the isostatic compensation starts with rebound movements until the equilibrium is restored. I will return to the rebound effect of the isostatic compensation from time to time in the following videos, because they are of fundamental importance for the functioning of plate tectonics. Everything is based on gravity. The Earth's gravity, which ultimately leads to the mountains being lifted up and oceanic plates being returned into the mantle. In the next video, I will start to discuss the different types of plate boundaries. I will begin with the diverging plate boundaries, namely at a rift valley. This time, thank you for listening, and I'll be happy if you stick around. I recommend continuing with the plate boundary overview video.